Alright, Assalamu alaikum. So today we're going to discuss the concept of potential energy as it applies to electric fields. Now the concept of electric potential and potential energy is somewhat tricky. And the approach that I'm going to use is slightly unconventional. So it's useful to pay some attention to what I'm going to say now. Suppose I have some box in which there is a lone solitary particle. Could be a charged particle of charge q. Now this is in a void. A void really means an area in which this particle is the only entity that exists. In the cluster of galaxies that we live in, which contains the Milky Way and Andromeda, there is a giant void available in which there is hardly any real matter around. So suppose we are in such an environment in which the only particle that exists is a charged particle. Now this charged particle can have a kinetic energy, K. Of course, it can also have what is called the energy of being, which is m naught c squared. However, we're going to forget about this energy of being because this particle always exists inside the void. So this energy is always there. But the particle nevertheless has some kinetic energy because of its motion. And we know that in the non-relativistic regime, the kinetic energy is given by half the mass of the particle v squared. That's alright. Will this particle have any potential energy? It's in a void, it does not see anything in its neighborhood, there's nothing around, it's just a solitary particle. The concept of potential energy only arises when this particle is interacting with another particle. When it sees another particle, for example, we have a potential energy when we consider ourselves in relation to the Earth, because the Earth is pulling us. We have a potential energy when we consider ourselves in relation to the Sun, because the Sun is pulling us. Mars is pulling us, Mercury is pulling us, Venus, Saturn, all of these gravitational objects, they are exerting a force on us. However, if you are in a state of void, that is, there is nothing around, there is no reference point, there is no other object in the system to which we can relate. Therefore, the concept of potential energy does not make sense. Therefore, the only energy this object can have is kinetic energy. Now, suppose there is some omnipotent being, some supernatural being that can exert some force on this object, which means that it can do some work on this object. So this box that I've written here is my system. This is my system. Anything that's inside this box is internal to the system. And the only thing that's inside the box is the particle, the solitary particle itself. Now there is some work that is being done by an external agent. And suppose that work is Wx. X means an external agent. Now what is this external work going to do? What is it going to do? It's going to move the particle, it's going to change its kinetic energy. So there has to be a change in the kinetic energy. So if I denote the change in the kinetic energy by delta K, this delta K is the final minus the initial kinetic energy. Alright? So whenever I write delta, it means final minus initial. So this external work is going to change the kinetic energy of this object. Still there is no concept of potential energy here because this particle is not seeing or talking to any other neighboring particle inside the system because there is none. Now suppose there is another particle, Q2, inside the system. Now what this particle does, it's a charged particle Q2, it can exert a force on this particle. So this particle, which is our test object, which we are probing, is experiencing some kind of interaction with the neighboring particle that is internal to the system. So when this particle interacts with this particle, this particle can exert a force, which is another way of saying that there is an interaction. This force can also do some work on this particle. So extra work could be done on Q due to Q. That should mean vertical. Alright, so this extra charge that is inside the system can do extra work on this particle. Alright. Now this work I denote by W internal. The W internal could also change the kinetic energy of the particle, because from the particle's perspective, it's only being supplied with energy, which would come from an external source or an internal source. So the change in kinetic energy could be due to external work, and it could be due to internal work. Now internal work is done by other agents that are inside the system, that are internal to the system with which this particle is interacting. Now what I would like to do, I would like to take this term to the left hand side, and I would like to write delta K minus W internal is Wx. Alright, I hope you do understand what I'm trying to say here is that this particle can interact with another particle that's internal to the system. This particle could do internal work on the system. I'm just calling it internal work. I can take this internal work to the other side of the equation, and this is what I get. Now this object here, minus W internal, which is the negative of the work done by internal agents, by other particles with which the test particle is interacting, I can call this delta U. So if I call delta U and identify minus W internal, what I would get is delta K plus delta W is equal to the amount of external work done on the particle. Hence, my delta U has been defined. So this is a definition here as minus W internal. That is the negative of the work done by internal forces. Now if this were a charged particle and this were a charged particle, and we ignore the masses of these particles, there's no gravitational attraction or interaction, there's only electrostatic interaction. So what kind of force does this particle see? Will this particle see a force? What kind of force? It's going to be an electrostatic or an electric force. So what agent is doing the work? It's the electric field that is doing the work. So W internal is the work done by the electric field. And minus W internal is just the negative of that. This delta U is called the change in the potential energy of this system. I think this class starts at 8 a.m. It doesn't start at 8:15. So there's a lot of disturbance when students come in for the first 15 minutes. It just distracts me. So I define my delta U, which is the change in the potential energy UF minus UI, as negative of the work done by the internal forces. This is the change in the potential energy. The electric potential energy, that is. This is something that's relevant to what we're discussing so far. Now let's look at an example and let's clarify this concept a little bit. Suppose I have two infinitely charged sheets. And there is a tiny aperture on each one of them. This is positively charged. It's an infinite sheet, thin. Whenever I say sheet, it means infinitesimally thin, no thickness. And this is a negatively charged plate. And there are tiny apertures in each of these sheets. And there's a positive charge, for example, a proton or some other positive charge of Q that is moving with a velocity V initial towards the positively charged plate and is aimed at the aperture. So what's, if I ignore this positive charge, which could be small, what's the electric field to the left of the positively charged sheet? What's the electric field here? It's going to be 0. What's the electric field here? It's going to be 0. The only electric field that exists is in between these plates and is pointing in this general direction. Alright? So there's no electric field here, there's no electric field here, and you can prove this by Gauss's law or the principle of superposition. So the electric field E is sigma over epsilon naught only in between the plates and is pointing a certain direction. So if this is my y-axis, it's pointing along J. This is my electric field. It's 0 here and it's 0 to the right of the negatively charged sheet. Now this proton is coming in with a velocity Vi. Nothing happens to its velocity in this region because it's not seeing a force. So it comes here, it's aimed at the aperture and enters this region. Now when it enters the region of the electric field, it starts experiencing a force because there's an electric field here. What's the direction of the force? Aap batao. जी जी ये क्या होता है? Along J. So it's along J. This is the direction of the force on this particle. Now what this force does is that it accelerates the particle. So the acceleration of this particle is given by F over m. The force is simply the charge into the electric field Q sigma over epsilon naught mj. So this is the acceleration of the particle. And what acceleration really means is that the velocity goes up. So the velocity, which is still pointing along the j direction, now becomes dependent upon x. Okay? So where x is a variable which starts from here and goes up to this, it just runs in this direction. So this separation, suppose it's capital L. So V now becomes a function of x inside this parallel plate capacitor. And what is this V? It's going to be the initial velocity plus the acceleration, which is this Q sigma epsilon naught m into the time j. So it moves a distance x in the time t. So this is the velocity as a function of time. I could also write this as a function of x if I use another equation of motion. Anyways, the velocity is increasing as the particle is moving from the left to the right because it's experiencing a force, because there is an electric field. Alright, now what's going to happen to its kinetic energy? Here the kinetic energy is half mvi squared. But now this force does some work on the particle. Now the particle has entered a region of the electric field. So it's interacting with the electric field. That electric field has been set up by these charges. So all of this drawing that you're seeing here constitutes a system. So the system comprises this positive charge and the infinite sheets of charges. All of these compose the system. Now there are internal interactions between the test charge and these large charged sheets, which means there is an electric field. That electric field does work on the charged particle. So it's interacting with other agents inside the system. So the internal work that is done on our test particle is simply the force that is exerted by the electric field that comes out because of the electric field times dx. And you take the dot product and then you integrate. If you would like to find out the total work done on the particle as it moves from the positive to the negative sheet, you'll have to integrate x, which is now the running variable, from 0 to L. So this is the total internal work done on the system. And this turns out to be now the force and the direction of the displacement dx are the same. So the angle between the force and dx is 0, cosine theta is 1. And the force is just constant because the electric field is constant. So the force is Q times the electric field sigma epsilon naught into dx integrated from 0 to L gives you L. So this is the internal work done on the test particle. But this also equals minus of delta U. This is something that we've already defined. So the equation that we're going to start off with is that the change in the kinetic energy plus the change in the potential energy equals the external work done on the object. Now what's the external work done on the object? How much work is done on the test particle by other particles that are external to this system? Nothing. There's nothing external to the system. All the work is done by charges that have been set up inside the system, by the electric field that has been set up. There is no other extraneous field that we're talking about. We just have an internal electric field. Okay? So this right hand side is 0. So we left with delta K equals minus delta U for this particular case. Now delta U is given, minus delta U is given by the internal work done here. So this equals Q sigma L over epsilon naught. So all of this is positive. Q is positive, the charge density is positive, everything is positive here. So this is a positive term. Delta K has to be positive. So what's happening is that as this positively charged particle enters this electric field region, it starts to accelerate and its kinetic energy goes up, its velocity goes up. So here its velocity is Vi and it just picks up its velocity and the velocity reaches its maximum at the negatively charged plate. So it gains kinetic energy. So if I were to make a plot, if this is my axis, this is x, this is 0, this point is L, and if I were to draw the kinetic energy on this axis, there is a starting kinetic energy, which is half mvi squared. Now the kinetic energy steadily increases. If I were to replace this L by x, the kinetic energy, change in kinetic energy is a function of x, and it's ramping up linearly with x. So it's ramping up linearly with x until it reaches L. Here the kinetic energy is half mvf squared, and this change in kinetic energy, delta K, is given by this, right? This is delta K, the change in kinetic energy. So now the particle has entered an electric field and its kinetic energy goes up. And it's all making intuitive sense here. The electric field is accelerating the particle, so its velocity must go up. This difference is the change in kinetic energy. But the change in kinetic energy is equal to the negative of the change in the potential energy. Now let's see what the change in the potential energy is. the change in the potential energy, delta U, is simply given by this equation. So it's minus Q sigma L over epsilon naught. So what's the change in the potential energy? Is U final minus U initial is minus Q sigma L over epsilon naught. Now this is a negative number here. Negative number means that the initial potential energy is larger and the final potential energy is smaller. So the potential energy is decreasing. And the change in potential energy, the negative of the change in the potential energy, which is a positive number, is the same as the change in the kinetic energy. So if I were to draw the potential energy on this graph, what would I draw? I would draw a downward sloping line which has the same slope as the kinetic energy. Alright? So I could draw a downward sloping line like this. Okay? So this is the change in the potential energy, delta U, magnitude, which is the same as the change in the kinetic energy, delta K. So what's happening here is that we have something similar to a spring mass system. Kinetic energy goes up, the potential energy goes down. And the sum of the kinetic energy and the potential energy remains zero. Zero is the external work done on the object, which is zero in this case, because there's nothing external to the system. So the equation that I've written at the top is just the first law of thermodynamics. Remember that. And I hope you learned some thermodynamics in your modern physics course. So the change in the kinetic energy is balanced out by a change in the potential energy. Okay? So the particle enters here, its kinetic energy is minimum, it ramps up, it reaches its maximum here, but at the same time the potential energy goes down. So you can also observe that if the charge is close to the positively charged sheet, its energy is highest, the potential energy is highest. It does not like to remain close to the positive charge because it's a positive charge itself. So it would like to flee away from the positively charged sheet and would like to decrease its potential energy. So it moves away from the positively charged sheet and goes towards the negatively charged sheet, and the charge may issue out of this aperture. So after the charge has come out of the electric field region, the kinetic energy then becomes steady here and the potential energy becomes steady here. The question is, what's the potential energy of this charged particle at the instant it enters the electric field? I started this graph from a potential energy of 0. Now I would like to ask, what's the initial potential energy? Why have I started this graph from potential energy equals 0? Yes. Right. So we assume that it wasn't interacting with anything else. So its potential energy was 0. But this equation that I've written here is an equation between changes in kinetic energy and changes in potential energy. It does not tell you what the initial kinetic energy or the potential energy need to be. So you can use any reference as you like. You can start this graph from any potential energy that you really like. Okay? It doesn't matter. It's only that the change in the potential energy has to be the same as the change in the kinetic energy. Alright, you had a question? It was the same question? Good. Okay, one question I would like to ask is, if I were to plot with respect to x the speed of this particle between 0 and L, what would this graph look like? Can you give it a shot? Can you try? This is incorrect. आप दिखाएं। ये सवाल मैंने इसीलिए पूछा है कि आप ये जवाब दें और फिर सोचें कि ये नहीं है ऐसा। एक्सपोनेंशियल v स्क्वायर है ना, मैं v और x की मैं पूछ रहा हूँ, वो v स्क्वायर एक्सपोनेंशियल नहीं होता। स्ट्रेट लाइन फिर कांस्टेंट, स्ट्रेट लाइन का आगे कांस्टेंट नहीं, स्ट्रेट लाइन नहीं होगी। Kinetic energy goes up linearly in the form of a straight line. It's going to increase like this, like a square root function. Why is that? Because Vx squared equals V initial squared plus 2a acceleration is a constant into x. Now if I plot between V and x, I take the square root of both sides, so I will have to plot with respect to the square root of this. So it's going to increase like a square root function, and it's going to start off at some Vi. Okay? If I plot between V square and x, I get a straight line, but V square is just the proportional to the kinetic energy. Okay? So it's linear between the kinetic energy and x, but it's a square root function between the speed and x. So if you would like to plot between the speed and x, you take the square root of both sides. It's not an increasing parabola, it's a square root function. And then it just steadies off here. Now we've seen quite a strange definition here, that is the change in the potential energy equals the negative of the work done by the internal forces. Now let's strengthen our belief in this formula. Alright? Let's see, why have we come up with such an awkward definition for the change in the potential energy? There has to be some reason behind it. And it's easier to understand this in terms of the gravitational potential energy. Suppose I have the earth, I don't have to suppose that the earth exists. So I have the earth here, ground level, and I have an object of mass m. And I release this object from a certain height L, and it just falls to the earth. So my system now comprises the earth and this object. In this system there is a field. That field is the gravitational field. In this system the field were the electric field. So I can describe all interactions in terms of fields. Here I describe it in terms of the electric field. So all the energetic considerations lie within the field. The field tells you everything there is to be told about forces and energy. The fields are sometimes they're considered to be real. Right? Fields are real. So this is a philosophical debate in physics whether fields or wave functions are real or not. This debate is called the reification of fields. But what happens is that the fields exert forces. So you can consider the fields to be real. Okay? So the only thing that is of concern here is a gravitational field, because that determines everything. And an object, a test object of mass m has been placed at a height L above the earth inside this field. Is there any external work being done on this object? No. It's just internal work done by the force of gravity, by the gravitational field. Now the gravitational force is pointing in the downward direction, Fg. And this object is falling down. So I can define a displacement vector dx which is also pointing in the downward direction. So the work done by the internal field, which in this case is the gravitational field, W internal, is simply given by F dotted with dx integrated over this entire length. Now this work has to be positive. Alright, this work has to be positive because the gravitational field is doing work. Alright, so this work turns out to be Fg, which is mg into L. Both of them are pointing in the same direction. Alright, so this is the work done by the internal force. It's positive. Now if I write my energy conservation equation, which is the first law of thermodynamics, I have delta K minus W internal equals the external work done, which is 0. But remember that this object here is also the change in the potential energy, delta U. So this is really minus delta U as well. बहुत देर कर दी मेहमान आते आते, हम तो आपका इंतजार कर रहे थे. So this means that delta K minus W internal is 0, which really means that delta K equals W internal, this equals mgl. So the change in kinetic energy is positive because the field has done work on the object. It has increased its kinetic energy. So the object was released from rest, its kinetic energy increases as it falls down. Okay, its velocity goes up. We all know that this is free fall. And if you talk about delta U, the change in the potential energy is simply minus mgl minus W internal, which is minus mgm. Now this is negative. So the potential energy of the object decreases. So here the object has a higher potential energy, a gravitational potential energy, and here it has a smaller potential energy. Alright? You have to be careful about the limits here. You would like to make all of this positive. So you would like to integrate from 0 to L instead of from integrating from L to 0, or you have to choose your dx properly in a direction such that this turns out to be positive. This is something you have to be careful because this is work being done by the field. Okay? And the gravitational force and the displacement are in the same direction. So this is something that you need to take into account. So all of this is making perfect sense. Here the potential energy is maximum and here it drops to 0. The kinetic energy is 0 here and it goes to its maximum value when it hits the ground. So the definitions that we've used, which are delta K plus delta U equals W external, which is thus the first law of thermodynamics. In the first law of thermodynamics, you also like to put in a term that goes as plus Q, where Q is the thermal energy that goes into the system. That's just the first law of thermodynamics, but everything is insulated here, so there is no thermal energy transfer. So this is just the first law of thermodynamics, remember. And you generally call this, you might like to call this the internal energy of the system. The potential energy is a kind of internal energy of the system. So if you would like to make a connection with the first law of thermodynamics. Anyway, so let's look at the converse situation. That is, now I have an object that's lying on the ground and I would like to lift this object to a height L. Now I am external to the system because I am external to the field. So there is some external work that is being done on this object. So now my first law of thermodynamics, delta K plus delta U equals the external work that I do on the object. Okay? W external. Now I would like to find out how much work do I need to do to lift this object. Suppose I lift this object such that its speed remains constant. This is my supposition here. I'm moving it with uniform speed up to height L, which means that the change in kinetic energy is really 0. Its kinetic energy is not changing. Now this is a quasi-static condition. It was at rest when it was at ground, and I'm moving it so slowly that it's always at rest with respect to my hand. It's a quasi-static motion. Alright, just keep this into mind. That is, when I'm lifting this object, its kinetic energy is not changing. It has some velocity here and its velocity is still the same as it moves up. Okay? So it's a quasi-static condition. The change in kinetic energy throughout the course of its journey is zero. Lot of subtleties here. So this is zero. Now I would like to find out the change in the potential energy. The change in the potential energy is always equal to minus W internal. This is what we've defined. Now this is equal to force. Now the force is being exerted by the gravitational field. The internal force is the gravitational force. Fg dotted with dx. Now the motion is in the upward direction, but the force of gravity is in the downward direction. So this dot product is negative. When this is negative, this negative sign, both of them combine to give me plus mgl. Remember, in the upward motion, my displacement dx is in the upward direction, whereas the force of gravity is in the downward direction. The internal force is in the downward direction. So the angle between these vectors is 180. So I have a cosine of 180, which is minus 1. That minus 1 interacts with this minus to give me a plus mgl. So the change in the potential energy is mgl. And of course this must be the case. The potential energy is going up. As this object is lifted from the ground through a height L, its potential energy goes up. So this potential energy goes up by mgl, but that equals the amount of external work that I have to do. The external agent has to do the same amount of work. So I have to provide energy mgl to lift this object smoothly so that there is no change in its speed from ground to some height L. And that energy must come from somewhere. It has to be supplied by my muscles, by the ATP, by the chemical energy that is stored in my arm, by the breakfast that I've done, right? So that energy must come from somewhere internal. So everything is neatly, tidily, coherently adding up here. The first law of thermodynamics, or the law of conservation of energy that we started off with, and the definition of the change in potential energy is all adding up neatly here to give you a coherent picture of what the potential energy really means. And we can apply the same ideas to electric potential energies. I don't know if we have time today to look at this demonstration, but I give you 1 minute of peaceful silence. Alright, now consider a point charge. Q. And there's another test charge, Q2, QT, a test charge that's placed at a distance R. With respect to Q. Okay, so the distance is R. Let's call this distance RA, in fact, RA. Now what we would like to find out is the potential energy of this charge when it's at a distance Ra from the charge Q. Now let's suppose, I would like to, okay, let me just fix this here slightly. Now if my charge is Q, of course there is an electric field due to it and it's pointing radially outwards. I'm at some distance Ra from this charge, Ra. Now I have a test charge. I place it at Ra and then move this test charge. Now what's going to happen if I place this test charge at Ra? This charge is going to experience the force exerted by the electric field. So it's going to move. Suppose it moves in some arbitrary fashion, so that it moves in this fashion, because if it were just left on its own, it would move radially outward, because acceleration is radially outward, the force is radially outward. But suppose I am holding it somehow, and it takes a tortuous path and goes to a new position Rb. Alright? This is always possible, correct? I can just hand hold the charge and move it inside the electric field. Now when it's moving inside the electric field, it is always experiencing a force that is internal to the system. That's the electric force, because there is this charge that is synthesizing the force. So there is work done that is internal to the system. And the change in the potential energy, delta U, equals U final minus initial, which is UB minus UA, the potential energy here minus the potential energy here. Now this equals minus of the work done by the internal forces, by the electric field. Now this is minus integral, the electric field does applies a force which is Q test times the electric field E, which is a function of R, and it's a vector dotted with dl. Now dl is the direction in which the path along which this object moves. So if this is my tortuous path, arbitrarily shaped path, it is comprised of small segments, each of length dl, and the vector is pointing in different directions. So the vector here is pointing in this direction, it's tangential to the path. The vector here, dl, is pointing in this direction. The vector here is pointing in this direction, here is pointing in this direction. So this path is made up of small segments, each of length dl, and it's a vector because it specifies a direction as well. So these are all the small dl's that make up this tortuous path. Correct? And this is the change in the potential energy. Now we already know what the electric field is due to this charge at some distance r. And we're going from Ra to Rb, right? So the initial value of the limit is Ra, the final value is Rb. You might be noticing that I'm going really slow today because this is a tricky concept. So now what I would like to do, I would like to plug in the value of the electric field. I know what the electric field is. So I just take this integral for ease of writing. I just shift everything here. I write minus qt Ra to Rb, and instead of the electric field I can write its expression. This is q over 4 pi epsilon naught r squared, right? And what's the direction? What's the direction of the electric field at some point? Radially outward. So I specify that direction by unit vector r. and I take the dot product with dl. Correct? Remember, I am preserving the sanctity of vectors here. The left hand side is a vector, the right hand side is a vector. Now I would like to find out what is r dotted with dl. Now I draw my tortuous path again. I blow it up a little bit. This is my test charge, my charge that is producing the field. Now at this point, the unit vector r is like this. At this point, the unit vector r is like this. At this point, the unit vector r is radially out. So at each point it's radially outward. Here it's again radially outward. But dl is constantly changing. So at this point dl is in this direction. So I'm denoting the dl's in yellow. Here the dl is in this direction. Here the dl is in this direction. Here it's in this direction. So the angle between dl and r, unit vector r, is changing from point to point along the path. Alright? So there is some angle theta which is changing from point to point along the path. Now if I draw one such point, I have an r vector. It's just a unit vector, remember. It has no, the magnitude is 1, and I have a dl. Right, some dl, and the angle is theta. Now if I would like to find r dotted with dl, it's simply the projection of this vector onto this, or this vector onto this. So let me take the projection of this vector onto this vector. This is what the dot product really means. So I take the projection of this vector on to the blue vector. This is 90 degrees. So this is the projection, right? This length here is simply the dl cosine of theta, right? Because this is the hypotenuse dl, so this length is dl cosine theta. What direction is this dl cosine theta in? It's along the radius. Its magnitude is dl cosine theta. Now what if this path was from RA to RB? Now each dl can be resolved into two components. It can be resolved into a component that is parallel to the radial vector, right? This component, which has a magnitude dl cosine theta, and it can be put. It will also have another component that is normal to the radial vector. All right. Now the electric field is along the radial vector. So the dot product of the electric field with this component is always 0. So you only need to consider the component of dl, the component of the path that is along the radius. In other words, if your path is moving tangential to the radial vector, it's moving normal to the radial vector, the work done will be 0. Only that component of dl, that component of the path matters which is along the radius. So what in effect, if you're calculating the work done by the internal field, you only need to consider that component of the path that is along the radius. Everything else doesn't matter. In order to simplify this argument, suppose this was my charge and I move from point RA, which is this point, to another point RB, and the path that I take is the following. I go straight along the radius, then I move along an arc, and then I go straight along the radius. I can take this path. Now in this path, there will be some work done over this length because the electric field and the displacement are always parallel. In this segment of the arc, the electric field is pointing normal to the displacement. So the displacement is normal to the electric field. So if I take the dot product of F with dl, it's going to be 0 here. So no work is going to be done in this segment. But there will be some work done in this segment because in this segment, the electric field and the displacement, the tiny dl's are all parallel. Now if I change this path such that instead of going along this nice radial direction and then taking an arc, I can make this path tortuous. I can make this path tumultuous. I can make it in an arbitrary direction. In each of these cases, only that component of the path matters which is along the radius. So this dl cosine theta is really equal to dr. How much do I move along the radial direction? Okay, dr is how much do I move along the radial direction. How much radius do I traverse? How much distance do I traverse that's along the radius? Only that component matters. So what I have here on this side of the blackboard is this dot product between r dot dl, which is dl cosine theta, which is the component of dl along the radius, which is just dr. So my delta u becomes minus q test charge, okay, let me write it here, minus q, the test charge from RA to RB, 1 over 4 pi epsilon naught, Q that synthesizes the electric field, R dotted with dl, it's going to be a scalar, it's a dot product, and that's just dr. How much do I move along the radius? Dr. So no matter what kind of tortuous or arbitrarily shaped path I choose, only that component of the path matters that is along the electric field. Because any path, any dl can be resolved into a component that's along the field and that's normal to the field. And whatever is normal to the field doesn't really matter. It does not constitute any work done. So this is my change in potential energy, delta U. I can solve this expression. Minus qt q 4 pi epsilon naught. Now I dr over dr. So sorry, there's an r square here. Dr over r squared from Ra to Rb. Delta U is now equal to minus qt q 4 pi epsilon naught. What's the result of this integral? Negative 1 by r. So this negative becomes a plus. I get 1 over r, right? From Ra to Rb. Qt q 4 pi epsilon naught 1 over Rb minus 1 over Ra. This is simply UB minus UA. Now if Rb is larger than Ra, Rb is further away from the origin, from the point charge. Rb is larger, this object is smaller than this, so this is a negative number. So if you move away from the positively charged point charge, your potential energy decreases, and so it should. If you approach the positively charged synthesizing charge, the positive charge, your potential energy goes up. If a test charge, which is always assumed to be positive, comes close to another positive charge, its potential energy goes up. And if it moves away from the positive charge, its potential energy goes down. And this is all making sense here. And if we look at this expression here, and if we identify the first term, this term with UB, that's quite a neat thing to do. So this first term is UB, is our definition of the potential energy at point B. And this second term here is identified with UA. So if you are at a distance r from a point charge, then your potential energy is going to be Qt Q over 4 pi epsilon naught r. Remember, potential energy is a scalar. So if I plot r and I plot the potential energy of at the point r, I would get a hyperbolic downward sloping line that has a 1 over r dependence. Alright? And another thing that you observe, the potential energy depends upon the test charge, because this is the potential energy of the test charge. Alright? So it depends upon the test charge. It's a function of the test charge as well as the charge that is producing the field. Alright? Suppose I have a molecule which has, like water, or some other molecule which has a plus Q1 charge on an ion, a plus Q2 charge on another ion, and a minus Q3 charge on a third ion. And Q1 plus Q2 equals Q3, because this is a neutral molecule. And the distance between these ions is, suppose this distance is R12, this distance is R13, this distance is R23. Then this is our system of interest. This system of interest will have an electric potential energy. Inside the hydrogen atom, there is a nucleus, a proton and an electron. This system of two charges has a potential energy. Here we have two charges. One is a test charge and the other is a charge that's producing a field. You can also consider this to be the test charge and the other one to be producing the field. It doesn't matter. The whole system has some internal energy which is called the electric potential energy, which depends upon the separation between the charges, inversely so. So this configuration of ions or inside the molecule will give a net potential energy. And each of these, look, it's a pairwise interaction. Pairwise interaction means you look at the interaction between these charges, and then you look at the interaction between these charges, and then you look at the interaction between these charges. And you can find out the total potential energy of this system. So the total potential energy that is embedded inside this system is going to be the following. U of the system of this molecule, I just take out the 1 over 4 pi epsilon naught, it's common. So I have Q1 with Q2 divided by R12. This is a pairwise interaction between ion 1 and 2. Then a pairwise interaction between ion 1 and 3. Q1 into minus Q3. Right? So I put a negative sign here. R13 minus Q2 Q3 R23. So if my test charge were a negative charge, the potential energy would work the other way around. Alright, so this is the potential energy that is stored inside the molecule in the form of an electric field. So the electric field, remember, harbors the energy. The electric field contains the energy. It has some density per unit volume. Everything is inside the field. Alright? Remember this. It's very important. And the potential energy is a pairwise interaction. You have to take into account both charges. Alright, another half a minute of silence before we move on to something really interesting. Ali, I'm sorry, this has to be done next week. Like static somewhere. maybe इसकी बात नहीं करेंगे. Alright, instead of moving on, let me show you a demonstration. I think it's better. So what we have here is alright, question. ये मैंने बड़े तफसील से बताया है क्लास के बाद आगे. Alright, so what we have here is a pair of plates. Both of them are metals and they are connected to a high voltage power supply. This is a supply that we built in the laboratory. It can produce about up to 15-20,000 volts. It uses a flyback transformer that's also used inside television sets. Now what I would like to show you is that if a large potential difference is built, and I'll explain what potential difference means, then this air, which is generally an insulator, it no longer remains an insulator, it breaks down. So if over a distance of 1 centimeter, the voltage is 50 kilovolts, the air would break down. So this is called the dielectric strength of air. It's just going to break down and behave like a normal conductor. And this conduction is now done not by free electrons alone, but by positive and negative ions as well as electrons. Alright? So what I'm going to do now is I'm going to turn on a power supply and I'm going to place a candle in between. Now this flame of the candle is a really interesting object because it drives our civilization. The flame is so important, Shola, that it drives our civilization. And how does it do that? Because this is what happens in an internal combustion engine. That's what makes our transportation work. That's what fires the boilers that produce steam to make electricity, to run the turbines. So it's this simple flame that actually describes why we exist the way we exist today. Now what I would like to do is now this flame that we observe is in fact, it has an internal structure. It has positive and negative ions, and those ions are coming from the wick of the candle as well as the air. So this air that we see has oxygen, nitrogen, and if the electric field that is exposed, the electric field that air sees is so high that the air's insulation properties break down, and the ions that are in the flame, they start moving. Since they are charged particles, they start moving under the action of the electric field in opposite direction. The positive ions will move in one direction, the negative ions will move in the other direction, and they will pick up kinetic energy, they will pick up velocity, and the kinetic energy is going to increase, and as the kinetic energy is going to increase, they are going to ionize other air molecules. So oxygen will be ionized, free radicals of oxygen will be created, and those free radicals can actually combine to give you ozone. The nitrogen can then react with the free radicals of oxygen to give you nitrous oxide, nitrogen dioxide. Sometimes you also get sweet smell from these discharges. Such a discharge is called, by the way, a corona discharge. And it happens near high voltage equipment as well. In our countries where the transformers and the connections are not really properly done, and there is sparking that you see. That sparking is the breakdown of the insulation properties of air due to the action of high electric field. So what I'm going to show you now is some strong ionic winds. So I'm just going to place this lit up candle which is producing these positive and negative ions inside a strong electric field. So this is candle in the wind. Ionic wind. Power supply on? This one. So don't try these high voltage experiments on your own. You really have to be careful. Alright, so I'm turning on the power supply and you'll focus on the candle, right? So as soon as I turn on the power supply is off. It's a nice vertical flame. The ions are all symmetrically disposed and if you just focus a little bit, what you'll see is that there's a positive region, there's a blue region of this flame, and then there's a yellowish region of this flame. So which region has the higher temperature? It's the blue region, and this is something you learn by Planck's radiation law. The blue color corresponds to higher average temperatures. So this is what the flame, it's vertically disposed, it's going up, the ions are all symmetrically disposed. Now I turn on an electric field. What the electric field will do is that it will produce an electric field either in this direction or this direction, I don't know. Right? But it's going to be an electric field that's horizontal. And that electric field will separate out this, or split this flame, bifurcate this flame into a positive stream of ions and a negative stream of ions. And those ions are coming not only from the flame but also from the air. And you might also see a corona discharge. This is a conducting path of ions between the flame and the parallel plates of the capacitor. Is this really a capacitor? Okay? Let me turn on the power supply. Alright, now what you see here is that the flame has moved in one direction, which means that the positive, suppose the positive ions are now being attracted to this negatively charged plate, and there's going to be a stream of negatively charged ions which are moving here. Now their color is just not right, their energy is just not right, we can't see it with the naked eye. Alright? So this is an example of an ionic wind. If I increase the electric field. Now I cannot increase the electric field. The electric field is just determined by the potential difference. Right? So if I decrease the separation a little bit, I can also increase the electric field now with my power supply. At some point the ionic winds can become so strong that they will blow off the candle will extinguish itself. Alright, I'm unable to do that in the present case, but let me try this in another fashion. What I'm going to do now is I'm going to turn off the power supply, and instead of these flat parallel plates, I'm going to use pointed needles as my conductors. So what these pointed needles are going to do is that they're going to increase the electric field in the vicinity of these conductors. And this is something we're going to learn. We were supposed to learn it today, but we don't have time. But if we have pointed conductors, the electric fields around those pointed conductors can in fact be really large. So I'm going to remove these plates. I'm going to replace them with pointed conductors. These are just syringe needles. नजर आ गई? I would also like to wear some gloves just for safety. Alright, I can extinguish this candle because the ionic winds can be so strong, and let's try to light up the candle. Now I'm not using a match, I'm trying to light up the candle because if there's an electric field, there is going to be a corona discharge or a movement of ions. They will pick up kinetic energy, and when these high energy molecules strike other molecules, they're going to increase the temperature of those molecules. So I'm going to see the temperature is high enough that it exceeds the flash point of the wick of the candle so that it lights up. I'm just going to try this. Now this is the corona discharge that you might be able to see. These are just moving ions. Alright, so I can also light up the candle. Now performing the same experiment with the flat conductors was difficult because the electric field in that case was smaller, even though the potential difference is going to be large. So what we're going to learn in the next course, in the next class, is what happens at electric fields near arbitrarily shaped conductors. We know that the electric field is always normal to the surface of the conductor, but what happens when the electric field can be enhanced beyond certain values, and how is that possible? Alright, so I'll see you on Tuesday, and best of luck for the quiz tomorrow. It's not going to be an easy quiz, by the way.